When discussing fission, we used a plot of the binding energy per nucleon to estimate the amount of energy released in the fission process. As we show here, the massive nuclei at the right end of the curve have a binding energy of about 7.6 MeV per nucleon. The less massive fission fragments are near the center of the curve and have a binding energy of approximately 8.5 MeV per nucleon. The energy released per nucleon by fission is the difference between these two values, or about 0.9 MeV per nucleon. A glance at the far left end of the diagram suggests another means of generating energy. Two nuclei with very low masses and relatively small binding energies per nucleon could be combined or fused into a single, more massive nucleus that has a greater binding energy per nucleon. This process is called nuclear fusion. When fission occurs, a massive nucleus divides into two fragments whose binding energy per nucleon is greater than that of the original nucleus, thereby releasing energy in the process. When fusion occurs, two low-mass nuclei combine to form a more massive nucleus whose binding energy per nucleon is greater than that of the original nuclei. A substantial amount of energy can be released during a fusion reaction. To see this, consider the fusion of deuterium, or hydrogen-2, and tritium, or hydrogen-3. When their energies are large enough to overcome the electrostatic repulsion between their respective nuclear protons, the two nuclei collide and fuse, releasing energy in the process and two products, a helium-4 nucleus and a neutron. We write this equation as follows. Hydrogen-2 plus hydrogen-3 react to give helium-4 plus a neutron. In order to determine the energy released, we must first calculate the mass defect. Before fusing, the total mass of the deuterium and tritium nuclei is 5.0302 atomic units. After fusing, the sum of the masses of the neutron and the helium-4 nucleus is 5.0113 atomic units. Therefore, the mass defect, delta M, equals 0.0189 atomic units. We can find the energy released by multiplying the mass defect by the energy per atomic unit, 931.5 MeV per U, giving 17.3 MeV in this fusion reaction of one deuterium nucleus with one tritium nucleus. Since the total number of nucleons is 5, 2 for deuterium and 3 for tritium, we divide this result by 5 to obtain the energy per nucleon, which is 3.5 MeV per nucleon. In comparison, the fission process of uranium-235 only releases about 0.9 MeV per nucleon. Because fusion reactions release so much energy, there is a considerable interest in fusion reactors, although to date no commercial units have been constructed. The difficulties in building a fusion reactor arise mainly because the two low-mass nuclei must be brought sufficiently near each other so that their short-range strong nuclear force can pull them together, leading to fusion. However, each nucleus has a positive charge and repels the other electrically. For the nuclei to get sufficiently close in the presence of the repulsive electric force, they must have large kinetic energies and hence large temperatures to start with. For example, a temperature of around 100 million degrees Celsius is needed to start the deuterium-tritium reaction discussed here. Reactions that require such extremely high temperatures are called thermonuclear reactions. The most important thermonuclear reactions occur in stars, such as our own Sun. The energy radiated by the Sun comes from deep within its core, where the temperature is high enough to initiate the fusion process. Human-made fusion reactions have been carried out in a fusion-type nuclear bomb, commonly called a hydrogen bomb. In a hydrogen bomb, the fusion reaction is ignited by a fission bomb using uranium or plutonium. The temperature produced by the fission bomb is sufficiently high to initiate a thermonuclear reaction where, for example, hydrogen isotopes are fused into helium, releasing even more energy. For fusion to be useful as a commercial energy source, the energy must be released in a steady, controlled manner, unlike the energy in a bomb. To date, scientists have not succeeded in constructing a fusion device that produces more energy on a continual basis than is expended in operating the device. However, the commercial use of fusion to provide cheap energy remains in the future.